All right, let's start with, put you down here, and go for review session. Hey, that's what we're here for, right? Well, welcome to the review session. We have a lot of things we could choose from. I have a lot of options for things we can cover today. I'm not sure if everyone, it's not the thing I wanted. Where's the thing I wanted? I had an equation sheet in here. I guess he disappeared. That sucks. Well, I'd like to have gone, had an equation sheet in my hand. It's not there. It's not there. It's not there. Oh well. Good thing to be using for the exam review to have an equation sheet. And check it out. Here is the sections on the equation sheet. This one might be a little out of date, but here's the things that we've covered. Over on the left-hand side, we've done particle kinetics, right? Particle kinetics, where we have F equals ma, work energy, and impulse and momentum. And a couple other things to help out with some power and efficiency, coefficient of restitution. Those are our three main topics that we're doing today. Ask yourself, I like talking to myself, and answering myself, it makes me happy. Particle, okay, Newton's second law. So that was class 6, where we did F equals ma, and we did in rectangular coordinates. Then we did class 7, in homework 7, we had path and polar coordinates. Particle work energy, we had class 8, where we used the potential energies, both the spring and the gravitational, the kinetic energy, the work added, and friction loss. And then class 9, we did a little bit more of it, but we also had conservation of energy, which we kind of did in class 8 as well, but we added power and efficiency. And then impulse momentum, we had class 10. Remember that the impulse is force times time, and if force varies with time, we might need to integrate to do that. But quite often, if the force is constant, or we want to find the average force, we just use delta T, force times time. And momentum is mass times velocity. And then in class 11, which many of you just had, some with you maybe, collisions, and then the coefficient of restitution. So up on, I'm not sure if, let's see, we have any Dr. Orlip students here? Right. We have Dr. Rico, right? We have some Dr. Rico, and then you have some Dr. Vito ones. Okay. I know I've posted practice problems. Dr. Orlip posted old exam problems that I lent them. I gave him. You see, okay. So just make sure you check Blackboard and see if you have it. You could email him and ask him if he. I think he has in the past. I put together a bunch of problems that when I taught the Coast Guard Academy that we used. So if you see right next to the problem, like S23, the spring of 2016 was when that exam question. I should mention that sometimes these exam questions can seem or even be easier than what you will have on an exam, because generally we would ask a lot of questions on a 50-minute exam. So by their nature, they had to be a little more straightforward. Where here, most of the time, I found I can only ask about 3 questions, sometimes 4, in a 75-minute exam. So here we might be getting a bunch more. So just bear that in mind right there. I've had legitimate complaints like, hey, the exam I gave was harder than this. This is merely to give you an exam type question and give you an opportunity to try to work through and organize your brain. But sometimes I have to combine aspects into a problem, so just bear that in mind. I have a number of problems here, but I like to kind of reserve these for you to do, right? And I really, I gotta beat this drum as hard as I possibly can. I know it's repetition, you're tired of hearing me say it. The best way to prepare for any exam is to simulate the exam, to take problems with a blank sheet of paper, and it's hard to have the self-discipline to do it, but it pays off so much more than just reading the solutions. And the hard part in exams, first hard part, identifying where to start, right? As soon as you see the solution, okay, that's a good place to start. But now you robbed yourself of the opportunity to get past that hurdle that we all face when you have a blank sheet of paper and a problem you've never seen before. I get overwhelmed during an exam. That's the pressure of the exam, right? They can often give you like, I have no clue absolutely what to do. In my room, it seemed completely obvious, but here on the exam, no clue what to do. So you have to practice that, getting over that hurdle. Write down the stuff that you know, right? Write down the things that you think it's going to be. Start with the things that you can do, right? Get some momentum going. And then you also have to practice the aha moment. We're looking for that aha moment, trying to find it. It might occur while you're reading the problem, but that's actually kind of rare. A lot of times it's going to be somewhere as you're working through the problem, you go, oh, I see what you have to do here, right? And you got to practice that. So practice the problems, work through the problems. So here are a bunch of ones, and there's also another resource I've made available. I can send you the link. It's on, if you're registered for this class, you also have what I find is to be a tremendous resource. It's the Missouri University of Science and Technology. This gentleman, actually, I don't know if it's a lady or a gentleman, to tell you the truth, here, but if you are registered for this course, under useful links and resources, you will find down below that, have I pointed this out before? I think it's funny that it's must. The Missouri University of Science and Technology must. And as someone that was in the military and found it was just ridiculous how many times we create an acronym and then try to pronounce the acronym no matter what. Like there's SYNCPAC and SYNCLANT. That's the Commander-in-Chief of the Atlantic and Commander-in-Chief of the Pacific Theater. And SYNCPAC and SYNCLANT, they're always talking about SYNCLANT, SYNCPAC. Anyway, give a dog a bone. That's what one friend used to say. But anyway, here is the must. He's got, look at all these. All these are questions. Every one of those things, like 1, 2, and 3 right there. Those are all exam questions, old exam questions. Look how many there are. That's a lot of exam questions. Here's entire exams right here that you can use. So I went ahead and just randomly grabbed some out of here, and I thought maybe, hey, that's what we might want to do. Work through some of those. But we can also pick out homework problems, stuff I like. You could say, I like this kind of problem. That's what I would like to do. Or pick one.
Do you choose your questions of the exam on that?
I have in the past, but that would take you a lot of effort. It'd be a lot easier just to learn the material, but you could probably find some. I believe I have picked a couple before. By the way, I also have, and I forgot to mention in our class, like one of the exam questions came right from one of the suggested problems in addition to homework. Because I thought it was a good problem. I like always trying to find that balance of, is this too difficult to take during an exam and that kind of thing? Does this measure people's ability to do a problem? Does it have any tricks inside it that seem unfair? Those kind of things. So yes, I have picked them before. Do we have any requests? Taking requests. Freebird is not one of the requests. Can't do Freebird. No Freebird. Yeah.
What about Stairway to Heaven?
Stairway to Heaven, no Stairway. No Stairway.
Well,
I am playing tonight though in Essex, so the band's playing and playing neither of those songs.
Can you hear some Floyd?
Can you hear some Floyd? I have Comfortably Numb on the set list, but on the back set list, but after that tonight.
If I were to show up and shout Freebird,
you would get one of these, no charge.
show up as
It's almost a reflex now. I used to play it when I was solo acoustic. Used to play Freebird just to punish the people who asked for Freebird. Long version. I know, totally throwing off base. This is being recorded too. What a great recording.
Sorry. So, with oral, we have homework 11, and it's a problem where it involves projectile motion and oblique.
Yep.
Force.
Hitting the wall.
Yeah.
Do we have something like that? That's a tough one for an exam question, so it's kind of tough to try to help out, but I know this is also a homework helping thing to do. Let me think of how to approach that. Well, I think here's one right here that's really close. Okay, yeah, this is pretty close, right? We're going bouncy, bouncy. So in that problem, I recall it, you have to do projectile motion, and just so you know, I think a really easy, a way to keep it organized is to do a coordinate transformation. You know, and then to break the things into normal and tangential. But that's the big idea in any collision, that oblique collision, is that you want to break the thing into normal and tangential. And the tangential, they just keep doing what it's going to do. So this is definitely an abbreviated, that's actually a pretty good spot right there. By the way, I don't have the answers to this, so. And I grabbed a bunch and then I didn't pay attention where I got them from. So I didn't want to like scour all the way through the Mustang. So we're just going to use the old Hewlett-Packard 35S, the engineer's calculator, reverse Polish notation. You should. No one's ever going to do what I asked them to do. That's totally fine. All right, so in any of these problems, I think it's a good idea, even if it's not going to be used and we're not going to use it this time, it's still, this is part of the thinking process to go to do these diagrams. Initial, impulse, and final. Because it's part of the problem, right? So we have the bouncy, bouncy happening right here. Here's the ground. Here's the impulse. And here is the final. And here's a coordinate system. And actually, this coordinate system, you know, if we're thinking about it, this is actually going to be the normal. Here's the tangential. And I've just decided to make, the normal actually could be downwards and might be, technically, that's the way that you would do it. But that's how I did it. So we know that we're coming down at an angle, but it has components going this way and that way. And we're going to go the mass of the ball, which is, oh no, it's a disc. It's a disc. Disc A. And we go VA1 normal. And we go MAVA1 tangential. And then we have an earth-shattering kaboom. By the way, I think anyone joining us via Collaborate is not going to see a damn thing, because they're just going to see what's on the screen. I don't know how to do that because I can't share that camera in there. They're just F. They're just F. There's nothing I can't do anything. I don't know. Anyway, so we have this impulse taking place. And once again, this is something we're going to find out that we can't actually use this right here. So the problem could have been done much simpler, much faster. Before I go any further, we recognize that in the x direction, or I guess in the tangential direction, as I've marked it down, that there's no impulse going on, right? No impulse, so what we will find is that the velocity in the tangential direction is going to be the same. And then right here, mass of A times the velocity of A to normal, right there. So, as I mentioned, we can't actually use impulse and momentum. But since it's an exam review session here, we want to make sure that we're thinking our way through a problem. If we're trying to be efficient, we could probably skip a lot of this stuff unless your professor absolutely has to see it. But recall here that we also have the mass of the world times the velocity of the world at 1, and the mass of the world times the velocity of the world 2. So if we have the total momentum, and then we only go into the normal direction, the ender, we get MAVA1 tangent, normal direction. I guess we're gonna go minus, because I made upwards positive, normal, plus mass of the world times velocity of the world, 1. We know that the impulse is equal and opposite, so it goes away, goes bye-bye. And then we're going to have MAVA2 normal, positive because it matches the diagram. And then plus mass of the world times the velocity of the world, 2. But our big dilemma is that we have infinity times 0 and infinity times 0, and that's meaningless. It isn't 0 and it isn't infinity, it's undefined. So all of that was unnecessary, but perhaps helped us think through. First thing we think is, okay, I know that this velocity has to equal that velocity, because I could do it in the tangential direction. I haven't written that, but we could do that in the tangential direction. So instead, I'm going to use coefficient of restitution. First, maybe, I'll go ahead and do this. So the core is going to be, here's the definition of the coefficient of restitution. We'll say the velocity of A2 in the normal direction minus the velocity of the world at 2 in the normal direction, velocity of the world at 1 in the normal direction minus the velocity of the world at, A1. And I make sure they got flip-flopped, right, in here. So that's an important thing. Fortunately for us, the world, it might be moving, but not in the sense towards that disk or away from that disk. That's good news. So we're just left with VA2 normal over VA1 normal. Okay, so this becomes sort of a simple problem, straightforward. The first thing you have to do to be able to, actually implement the thing is to break the velocities down into VA1 into components. So we could say in the tangential direction, we're going to have 50, and I really, really dislike the 3, 4, 5 triangle because it gets my brain hurting. But I think we're going to go 4/5. Is that right?
Yeah.
Cool. So in my head, I want to say that's 40. Is that correct?
Yeah.
Yeah, 40. So we have 40 inches per second. I've resisted the urge to use my calculator on that, but trust me. No. 1 normal. And we could say that it's going to be negative. Well, we don't have to call it negative, but we called it, we established what the sign convention was right there and on the diagram. So we're going, it's going to be downwards. And so that's going to be 50 times 3/5, negative 30 inches per second. So we know that this right here is also equal to the velocity of A2 in the tangential direction. And so we can apply the core and take, what is he? Oh, that's shown at the bottom. He's 0.8. So we have 0.8 equals negative VA2, which we don't know, in the normal direction, divided by a negative 30. So we have VA2 in the normal direction. Is this going to be, 30 times 0.8, which I can almost do in my head. I think it's going to be 24. Is that true? Is it 24? And so now the thing being asked is the speed at 2. So we'll get VA2 is equal to, we'll take the components, we'll take 40 squared plus 24 squared. 40 squared, 24 squared. That's 46.65 inches per second. And then the angle, just inverse tan of rise over run. So the normal is going to be the vertical position. So that's going to be our 24 divided by 40. That's the run. And we get, that ain't right, 24, 40, minor radians. That still don't look right. There you go, I guess so, 30, yeah, 30.96 degrees. So that's what was being asked for in the problem. I like to just reinforce that, you know, the vector notion right there. So I would say a complete answer was 46 point. See, this actually rounded up to the 5, so I don't like rounding up to the 7 if I round it up to get to the 5. Doesn't matter really all that much, but inches per second, and we know it's going to be in that quadrant right there, and it's going to be 31 degrees. So there you go. That's how I would prefer to see the answer, but they asked it in stages and things. When it comes to the problem that you're referring to, where we have this going on right here, and we what you want to do is, you know, do your projectile motion and zoom in on there and establish that you have like a normal coordinate, and then of course they have a tangential coordinate. And then it even though it's not everyone's favorite thing, if you just grin and bear it, and you can do a coordinate transformation from the I and the J, because you're going to have a horizontal component and a vertical component right there. So do the coordinate transformation, turn it into the N and the T, and then you're basically doing the same thing here for the N, and then coordinate transformation it back into I and J. I know it's but if you just get used to it, it's not, you know, it's not torture. And then you do another projectile motion off the thing. So,
oh, sorry.
Go ahead, no, go ahead, please.
No, I was just wondering, why is the velocity A1 tangential equal to the velocity A2 tangential?
Great question. It's easiest to explain it right here, right? If we were to just zoom in and treat the ball by itself, most of the time when we're doing collisions, we're including both the particles. But we can do just one of the particles. So if it was just the disk by itself, and you were to put it on there, this impulse would not be equal and opposite. It would exist there, right? If I were to draw that out right there. And so we would have an impulse happening here. But in the x direction, we'd have no impulse. So nothing can change the momentum in the x direction. So the mass times velocity in the x direction 1, mass times velocity in the x direction 2, they're just going to equal to each other, and the masses cancel out, so the velocity has to be the same. One of the reasons why we said no friction. If we had put a spin on it, like in tennis, especially, I don't know, is it on the French Open? It's on clay, right?
Yes.
So maybe Wimbledon. I can't remember which one, but the spin of the ball with the fuzzy ball can actually have an impulse that changes what angle it's going to go, right? Because now that would influence what this angle is going to be, because this would not be true right here. It would be slightly true. You could have backspin, side spin, other things like that. But in this case, we'll call it smooth and say there's no friction.
So rule of thumb is that if there's no impulse involved, the direction of the velocity is the same.
Yeah, I think that's fair to say. And in this case right here, that's also the same thing true in the tangential direction, which is aligned with the wall. I don't think Dr. Orlip would mind me giving that away. What do you think? Another kind of question?
Can we do like a work energy one?
Sure, absolutely. I have a few on here. We could take it from one from the practice exam, or we could take it from a homework, which of course is going to be too long for an exam problem. Or we could take it from must. I'm going to write him a letter of thank you. Or we could take it, oh, there's another good one. Try and remember, is it Purdue? I want to look this up real quick. I want to meet the dude that writes these exam questions for one of the colleges I have. This guy must be a fun dude to hang out with. I mean, if you're that kind of person. Let's see. Cal Poly, acronym. Ooh, I don't have it on here. It must be only in my class. I'll share it with the recitation people as well. I like this guy. He had like a lot of problems with Captain Underpants involved. It's a lot of this dude is fun. Is it not Washington University? I think it's Washington University in St. Louis. It could be Purdue. Purdue has some good stuff, by the way.
But the WashU one has some of these are hilarious.
Yeah, some of these are hilarious. Right. So this guy, I can't figure out. I think it's my recollection is Jenin. I think it's the Jenin guy that's doing this, where he has. Oh yeah. Okay. So all of these are like continuing stories. All of them. I can't say that they're all kind of fun. After getting away with scheduling dynamics, the university invites Alberto Gonzalez to campus to unveil an expansion of his human rights violations, beginning with the version of the waterboarding in which the watery slime mold from the men's room in the CEC is allowed to grow over the floorboards of the entire engineering complex. An international observer, who weighs 50 kilograms, runs at 10 meters per second, jumps into the inverted table and slides. What is the coefficient of kinetic friction?
Something tells me.
And then, of course, the thing just keeps going on, and it's sort of, you got hanging right here, a squirrel from the great rodent welfare state surrounding Graham Chapel protests Gonzalez effrontery to the Western Moors. This guy just is entertaining himself. He just is having way too much fun.
Something tells me that his mom probably did not let him out of the house for a while.
He has fun. So anyway, I encourage you to use those. But I think the must problems are kind of a little bit maybe more practical in terms of your exam review. But I don't know if maybe some people might get like a case of the giggles and then fail the class, and that would be good. Here's one that you're not supposed to use work energy on, so that's for must. But there's a lot of spring ones. And this is a complex one. I actually was thinking of using this one for the exam. So where did vertical. Anyway, shown. Do you want to do this one?
Sure.
Okay, sure. I haven't done this yet. I don't have an answer. By the way, I don't know if the other answer was correct. We'll never know because there's way too many to check. Shown below is a pair of blocks. Boy, do dynamics like blocks. Sure, like a cylinder sometimes. Just mix it up. Shown below is a pair of blocks. Block A on the frictionless horizontal surface has a mass of 2 kilograms. It's frictionless. That's nice of them. Block B is especially nice because the normal force would change. If you look at this problem, the normal force would change with the position everywhere in here. And that would be a pain in the ass because now the friction force is going to change everywhere with its position. So that's not very good. We could do it. It just during an exam, it would be a pain. It would be a pain. So block B, suspended by the cables, has a mass of 3 kilograms. The spring has a stiffness of 500 newtons per meter and an unstretched length of 400 millimeters. If the system is released from rest in the position shown, that is that oh, x is equal to 800 millimeters, determine the speed of the block A when x is equal to 0 millimeters. This is a dangerous problem if you're a professor, because you could make the numbers so that it goes the other direction. But so they must have made B light enough that it's going to go to the left, right? And even then, I think in practical terms, it would be hard, I think, to actually get it. That spring's got to be some serious stretch to be able to get it so that it goes up. So what's the unstretched length of this? Say 400 millimeters. Well, all right. I'm just thinking from a practical terms, looking at things, but we shouldn't be distracted by that on an exam. He says, who gets easily distracted. All right, so I like to redraw the problem. I know this is not the most efficient way to go about doing things, but this is my method, how I think. It helps me to piece the thing together and understand what is actually happening. And my aha moments usually take place as I'm drawing the thing. Doesn't have, I don't think everybody has that same type of, it doesn't necessarily work for everybody in the same way, but that helps me get my head around this thing. All right, so here you go. Is that it? Can't read that. 600 millimeters? I'm guessing it's 600 millimeters. Don't care for millimeters, don't you? Just don't know where that comes from. Maybe some. Make sure you sign in. Want credit for being here. Credit for showing up. K is equal to 500 newtons per meter. And we label that A. He's B. He's 33 kilograms. And what is he? Can't really see. He's 2 kilograms? Yeah, 2 kilograms. MA is 2 kilograms. And stiffness, I think we have everything. All right, so I might, even though it's a simple problem, I recognize that it is a dependent motion problem. So I'll call that SA, and I will call this SB. Just to put those together, and then I'll take the length is going to be SA plus 2 SB. And then we know the velocities are going to be related this way. So the velocity of A is equal to negative 2 VB. I don't care about the negative, especially in a work energy one, because it's going to be squared, so it doesn't really matter here. One thing to note also is that if you would multiply by delta T, you'd also get like delta XA plus 2 times delta YB. So you could say that delta XA is equal to negative 2 times delta YB. Once again, I wouldn't rely on the signs. We don't need the acceleration, because we're going to use work energy for this. And by the way, we know we have to use work energy, or it's better to use work energy, because it's going to move between 2 different distances. Whereas Newton's second law is 1 instant in time, right? It's instantaneous. That's where the thing is located. We can use Newton's second law if it's constant, because we can get the acceleration and use kinematics. But this right here, the spring is changing force. So the acceleration of this is not constant, because the force isn't constant, right? So we have that taken care of. We assume by the way that this thing is, so if I were to have planned ahead, I might do a better job of drawing this out, but that's not too bad. This is state 1 and this is state 2. And then like up here somewhere, this is state 1 and this is state 2. So it makes sense to make this the datum. So it's at the start, the potential energy, at least due to gravity right here, is the gravitational potential energy. It's going to be 0 at state 1, and then it'll be something more right here. So this is going to be the delta Y of B. And we could also say that this right here is really going to be the delta x of A. Another thing we might want to take care of right away is to take a look at, because we see a spring, and the spring we know that we're going to need to have the amount of stretch. So at state 1, we're going to have the square root of what did we say that? Oh, that was 800, right? 800 millimeters. This, where does it start? So I'll have. We might as well put it into meters because we're not going to use millimeters for our calculations. So we go 0.6 squared, right? But we need to subtract out the unstretched length. So 0.4. So that's where it starts out. You probably could do this in my head, right? Because that's a 3, 4, 5 triangle as well, right? So it's like is this going to be equal to 1? Yeah, it's equal to 1. So it's going to be 0.6.
Where did you get the 0.4 again?
The 0.4 is the unstretched length right here. So this right here is the length at 1, and this guy right here is the unstretched length.
Gotcha.
Why do we subtract that out?
Because we want to figure out how much it's been stretched.
Oh, okay.
I love that sound, by the way. Oh, it's my favorite sound.
Thank you.
Thank you. No, try to memorize every one of those problems, okay?
Wait.
I hope I didn't just like act like that. I wasn't a jerk just now, right? No, okay. I can't tell.
Memorize all of them?
You at least did something.
Maybe a little.
And then we can do this one in our head, right? So it is 600 or 0.6 is going to be the length when it gets right to there, minus our 0.4. All right, so we've got a lot of our preliminary stuff, and we could have done this preliminary stuff at any point along the way, but sometimes it's nice. It's just if you recognize that you need the thing to do it before you start. So I will write out my main equation, KE1 plus PE1 plus U1 to 2 is equal to KE2 plus PE2. And I'll start down. Starts at rest, magical words, meaning 0. We do that so often that I kind of have a penchant for giving something an initial velocity, because it's like, we never give it initial, but I don't know, just me. PE1, we recognize that we're at the datum, so we don't have any gravitation, so we picked that on purpose. But we do have some spring potential energy. It's stretched. In fact, that spring is really the thing that's going to be motivating this thing to go. Without it, it'd go down, right? So it better be stretched out. So it better do something right here, because it's going to have to create some potential energy here. So see, 1/2, and the spring constant is 500. Be careful with units. So we're good here because we have 500 newtons per meter, and we're going to use meters here for 0.6. And I'm just being obnoxious using the 4 sig figs because it's just a reminder. I don't think that's obnoxious. And the units of work in SI is Newton meters. We have nothing going on externally because there's no friction, and there's no like hand of some mysterious person pulling things or whatever. And then we can go down to kinetic energy. This is the guy that we want. We note that we have 2 particles, so we can't forget that we have you know, it's the entire kinetic energy of the system. So 1/2 MA VA1 of 2 squared plus 1/2 MB VB2 squared. So we can stick in values that we have here. I like to do that. So it's going to be 2 kilograms. And what are we trying to find? The block of A. All right, so we'll stick with the VA2. And then here, we have B, who is 3 kilograms. But we're going to substitute in that he is going to be, that doesn't seem right. Should be, yeah, you know, yeah, 1/2, right? Yes, 1/2. Yeah, VA2. So 0.5 squared. Yes, that's right. I had to write it down. Okay, don't judge me. Don't you judge me. And then, oh, I could do that 1. So I think I got this right. 1.375 VA2 squared. And then lastly, PE2 is going to have both parts. Easy to forget this as we're going through, right? So we're going to have to do that little thing, double check ourselves as we're going through. And you know, that's one of the reasons why I like to write them as a list, is I'm isolating them and thinking about them and only them, as opposed to writing them out left to right. This strategy really helps you make sure that you don't overlook something in your haste, right? You want to be fast, but pause at just the right moments so you don't miss out on something. Because just having a brain, whatever, looks identical to missing a concept, right? And leaving, if I were to leave out like that it has spring potential energy, well, I just forgot for a second. Well, that looks identical to not realizing that it was there. MB G delta YB. By the way, we could have calculated delta YB somewhere up here because we had it up here. So we had delta YB was equal to 1/2 delta XA, which we knew was moving how much? 800, right? 1/2 times 0.8, so we have 0.4 being obnoxious 4 sig figs meters. All right, so 1/2, 500, and here's our 0.2 squared plus, we're gonna have 3 kilograms, sure. 9.81 for gravity. And then the distance it will rise is gonna be 0.4 meters. So 0.4, 9.81 times 0.2. And I said that's going to be 21.77 Newton meters. And so we can backfill into the thing that we want to try to get. 0 plus 90 plus 0 equals 1.375 VA2 squared plus 21.77. So another reason to do this in the in-between numbers is we can kind of see the cause of the motion is the spring, right? If this were to be larger, then it would become, we'd have to take the square root of a negative. And what we would find is that actually it couldn't be done, right? We just have set up a problem that's not possible to do. But we can get the VA2 is equal, so we'll subtract out from 90, divide by 1.375, and take the square root And we're predicting this is going to be at 7.044 meters per second is going to be the speed. They ask for speed, so you don't need to make it a vector. It's a good problem for an exam, because it has, you know, when you start out there, it's got a little bit of a, you know, some amount of puzzling things to it, but you got to think your way through, pay attention to some details, look at the fact that the spring has it's in a different direction, that kind of thing. Does anybody have questions? Complaints? Exclamations?
I did miss, why was work 0?
Because there was no friction, and there was no hand of deity or any ones that are pretending to be moving the thing, right? There's no external forces. So I always think of this as an external work acting on the thing, whether it be from stealing energy away like friction or putting energy in with an external force. We have requests. I'm playing for the first time tonight. See, my daughter says, yes, I know that song. Safety Dance. You ever heard Safety Dance? Really ridiculously silly poppy song. I'm like, we don't have a keyboard, so we're just gonna play it as like a punk song. It's just a silly song. I think it only became like popular because it had a weird video that stuck out on MTV. It's part of your education. It's really important that you learn those things. Really important. Extremely important.
Can I request Iran?
We do play that.
Oh.
Yeah, we play.
Who about
Good
Devo?
choice. No, Devo. I like singing, so this is mostly talking. It's Devo.
What about,
Talking Heads.
I want to burn down the house. I want to play that, but I can't. There's a high part that I can't sing.
Rush, Tom Sawyer?
No Rush.
No wrong?
It makes the drummer and the bassist way too happy, and you can't have that. Can't have it.
That's
And,
the
and
point.
Getty's voice is just like, I like every part about it except his voice. Okay. I'm sorry.
Could we do Need Second Law of Power?
Absolutely. That's okay. Actually, I don't know if I have one that's set up for that. I do have a couple that I want to cover because I don't think we've done them. So Newton's second law, just note, the car sliding is a classic problem. I don't think we had a homework like this. Did we? Okay. The tether ball, I always think it's the tether ball problem. Or you can think of it as the hammer throw problem, or whatever you want to call it, type of thing right there. That's also a problem because there's just a little twist that you wouldn't necessarily see on an exam unless you had like covered it onto the thing. There are example problems, so make it fair game. There are example problems in the book. Just remember that you are expected to own and use the book, right? I think I did my first semester teaching ever. I was using the examples in the book and was chastised by some students that they wanted to keep those to themselves. They want to see other problems. So I always gave other problems than the examples in the book, assuming that you would have the book and that you would use those examples. So that's just make sure you know that's part of the whole process. But anyway, I'll try to find, let's see if I can see, I don't know if any of these problems have power in them. We could always convert something into a power problem. Like we could do the problem we just did and say how much power is, but of course we don't have anything external, so that makes it kind of a little weird, right? But we could say how much power is the spring generating at that point. But we'd have to use Newton's second law in the position. That's not a good example. Tell you, that right there is just a terrible example. So never mind, because all of a sudden it's horizontal. Remember that in order for work to happen, the force and the distance it's moving have to be aligned with each other. The same thing is true with power. the force and the velocity have to be in the same direction. So at that instant, the spring was not doing anything. Like we could isolate the spring in the other positions and say, okay, well, even though it's pulling downwards right here, it's only the force of the spring in the position of the velocity. So you can't do that. Sorry, bad candidate here. I did have a impulse momentum one that I thought from Must that I thought was kind of interesting right here, because this is sort of a power one. So we could do this, but this is impulse and momentum with power.
That's fine.
Okay, cool. I just, I take requests, I try to, but I get weird requests as in a band. I get like really weird ones. Like someone wanted a Neil Diamond song. Like, are you even listening to the music we're playing?
Yes.
And they wanted a Neil Diamond, but I was thinking about just, we're coming to America. That's the only part of the song I know. It's just one chord. All right, so we have an impulse momentum problem, and we know we got a little graphy over here, which makes me scared because there's calculus involved. So a winch exerts a tension T, and I don't like it when they use the T. My name starts with T. I don't like that they're using T. F sub T. I'm going to change it to F sub T. F sub T right there. T should be torque or something. We don't want kinetic energy in the book is T. Like, on a cable which varies with time as shown. At time t equals 12, little t equals 12 seconds, determine the speed of the block. It starts from rest. Does it start from rest? It doesn't say, but it's on the ground, so it must be starting from rest, right? So, what's up with these pulleys, man? Somebody somewhere that started the whole dynamics thing. What I really like? I like pulleys. I'm a pulley person. I really enjoy pulleys. Right there is where we're taking our little graph. Sort of like those people who are train enthusiasts. Never understood the train enthusiast. Like not them like model trains. They like to go out and look at trains. Train spotting, that's a thing, right?
Ted Sussman.
Is Ted Sussman a train guy?
Oh, yes, he is.
I don't
Pretty
have.
sure he's caught.
Is that on Showtime? Is that what is that? Is it on Apple Plus or something? What is Ted Sussman on? No, you talking Ted? Oh, I was getting confused with what's the TV show?
What is Ted Sussman?
What is the TV show with the soccer coach?
Ted Lasso.
Ted Lasso. I know Ted. I know Ted Sussman. I'm sorry. I was thinking Ted Lasso, but he's a train guy. Well, it's not. I won't pick. I respect him. I don't want to pick up. I was going to pick on Ted Lasso. Totally down with that, because that's an imaginary person. So we have 60 pounds. Okay. So this right here has the units of pounds and units of seconds. And so, okay, so good place to start, unfortunately. Let's say we have S, and what is this guy called? He doesn't even have a name. Let's call him B. And let's call this one right here SA, right? We want to pick a location. We have to pick a location. The only way that in reality, that you can find a force does not exist unless you cut something. Thus the free body diagram. You can't see the force. You have to cut it. Well, you can kind of see, so a lot of times they show an external thing, but what they're implying is there's something you can't see that has been removed. Forces are internal to a thing. So you can't see tension. So it's actually, we cut the thing and then we can see the tension. Because if we cut the other side of the thing, right, the tension's going that way, right there. The tension's inside. It's hard to say. But anyway, so what we will do for this is, I'm sorry, back on track. So we have, call this SB. So L is equal to SB, 2SB plus SA. So therefore, 2 times VB plus VA. something we might want to use later. Yeah. So set up our impulse.
Thank you.
What was that? Initial. This thing gets in my way. I hate you. Initial. It's like taunting me. And final. I just spelled final wrong. Final, and start out with this guy. No, I don't need to draw him yet. And I would say this is integral of f. We go 2 times the integral of ft dt. And also, by the way, we also have mg delta t is going to be equal to that right there. And we'll make him go v m, oh, losing it. I didn't eat lunch. mb vb2. Sure. Okay. So underneath this summation of momentum, impulse equals summation of momentum afterwards. X and Y direction. So in here we're going to have 0 plus, all right, now we're going to have 2 times the integral of 10 times the square root of 3t dt. Because that cable, yeah, that's gonna get us the right thing, right? And it's going to be equal to the mass, which is the block is what, 60 pounds? Divided by 32.2 to get it into slugs. And that's going to be VV2. So let's see, what's my strategy here? We're going to take 20 times the square root of 3. T to the 1/2 dt is equal to, I'll just write it down again, I'll do the thing later, 32.2. And by the way, this right here is going to be, except for the 2 part, right? This is the tension right there, but we're dealing with tension that's right here. But we're going to find the area. So this is really going to be 2 times the area that's underneath that right there.
What's the mg delta t in impulse? What about that?
Oh, I forgot. Thank you. Humiliation. Why don't we just get rid of you? So we're going to put the weight in there, so instead of mg, and the t is going to be what, 12 seconds?
Wouldn't it be minus?
Double humiliation.
Double humiliation. Why? Oh, I know why. I never learned to read. No. Losing it. 60. It's a Friday.
Sure.
Every day's Friday at McDonald's.
Is that true? I worked at McDonald's. There were a lot of non-Fridays.
You know, it's 5 o'clock somewhere.
You know, there was a good motivating factor to get a college degree by working at McDonald's. It used to make me jump in the dumpster to crash down the trash, right? But that was not the most humiliating thing. Cleaning some of the bathrooms. And I live in Tennessee. And some people, I think they lived in the mountains, decided to come down from the mountain every now and then just to use a non-outhouse. and something would happen, and I don't know what it is, but I don't know how you can get mess this high up on the wall of a stall. How do you get your stuff that high up?
They just do it.
Motivation to go to college. They just had a try-hard spirit, right? They just, you know what I'm going to do? Okay, back to this.
South, they use spikes.
Something was going on. That's all I know. Let's figure this one out right here. We had 20 times the square root of 3, and then what we're going to go is 2/3, right? 2/3, because this has to be t 3/2. Is that true? Did I do that the right way? Come on, you people have better calculus than me. You had it more recently. I've had to relearn so many math things that I blissfully forgot. I think I made a mistake here.
Yeah, it's not 2/3, it would.
You have to go the inverse, right? Like if you raise it to t squared, you have to go 1/2 t squared if it's to start out with t, right? So you have to flip the thing upside down.
I think that's 20 on the outside of the integral.
It's 10 times 2.
Yeah, 10 times 2.
20 times the square root of 3 times t.
Yeah, I need the square root of 3.
No, that's the answer to the integral.
Oh, say it again?
20 times the square root of 3 times t.
Okay. I just want the number now. From 0 to 12.
Oh, hold on.
From 0 to 12. Let's kill this thing. I need a calculator. I could have done it.
Uh-huh. All right. It spit out 415.6921.
Well, you just go 7.
Yeah, I'm done. Yeah, 69.
All right. So 415. 4. Oh, yeah. It's entertaining. I can tell you. Minus 60 times 12. Let's hope that's less. Yeah. That's not. What did we do wrong?
Hold on. 2 times.
We're taking 12 to the 3/2, right? 3/2. So we raise that, and then multiply it by 2, divide it by 3, multiply it by 20, and then multiply it by the square root of 3. So I got 960.
Okay.
Anybody want to challenge my 960?
Give me a second, I typed it into my calculator.
Did you get it?
It's taken, it's thinking.
It's thinking. How old is your calculator?
It's a TI at 36, so.
Okay, just
960, yeah.
Wee-hee! Yay for getting something right today. 32.2. You know how do I get points for being brave? I guess you get brave points, right? So we have 12.88. Nope. 128.8 meters per second. I just did that. I'm sorry.
There's also the 60 over 32.2.
Yes, I put that in there. I'm sorry. I just forgot to write it down.
Yeah, 960.
What the? So I end up getting 128.8.
Oh, I forgot t. That's why.
Okay, cool. But this is the speed of the block.
And it wants the speed of the block.
Did it ask for the speed of block?
Yeah.
Oh yeah, oh yes, it does. Okay, but we wanted to make it a power problem.
Right.
All right. So the speed of the cable is going to be twice, right? Going back to here. Is that true? Yeah, because we just got VB, so we want VA. Don't get hurt, man. Okay. You okay? So we're going to get VA is equal to 2 times, you're still in there, still in the stack, 128.8, and get 257.6 meters per second. But now we need to find what the tension is at this time. But that's at 12 seconds, right? So the tension is going to be 10 times the square root of 3 times 12. So we will have, I don't know why I had to do that. 10. I think it's 60.
Yeah.
And it's a Newton. So now if we want power, we're going to take that Ft times the velocity. And it's because of this right here. Because this right here, this is the velocity, the VA. And because of that right there, we can find the power that's being put into the system. If you do this way right here, notice that they're opposite from each other. But that's because that's the power being extracted from the motor. So the motor can put power into the system because it's positive, or the system can be robbing power from the motor. You can think of it that way. It'll be negative. Like the directions actually matter. So the 257.6 and the 60 right here is going to give us 15,000. Oh, do something wrong?
Yeah, how is this in pounds and yet we're using meters per second? I have issues with that.
And also, how did we get over to the tension being in newtons?
He just felt like it.
It's rock and roll, man.
Yeah.
Sometimes you feel like a nut, sometimes you don't. This would be one of those no, this wouldn't be the nut days. This is definitely a nut day. So this would be pound, feet, or foot-pounds per second. And you might remember that the conversion for horsepower is 550 foot-pounds per second per horsepower. Good one to memorize. That's a good thing to know for the rest of your life. Store it in your pocket. So just divide it by 550. And one good reason to do that is then you can kind of like get sort of a, I don't know, maybe it's also nice to have in your pocket some amount of perspective on how much is 28 horsepower. Well, could be a small little motorcycle, not crotch rocket, but little dirt bike.
200 cc's.
A really, really, really big lawnmower. We're talking like industrial mowing the golf course lawnmower. Yeah, that's definitely not a car. One of those Yugos. I don't know. Yugoslavia doesn't even exist anymore, does it? Yeah. There was a Yugo. It was made in Yugoslavia. It's like a 3-cylinder engine.
Yeah, but what about Lucar?
Lucar. Oh yeah, Lucar. I actually had a Matchbox Lucar. That's how.
The PLP 50.
Say again?
The PLP 50
Not from me.
is the world's smallest car.
Oh. Challenge accepted. Let's make a smaller car.
It has 3 wheels, so.
You would be out the sunroof if it had one.
Just all the Europeans.
Let's see. Let's pick another because we're here and I'm so easily distracted. Oh, we have another 49 minutes.
You can always end early.
No, I've contractually obligated. I did this voluntarily, but this is voluntary. I just think it's the right thing to do. I had professors that gave me exam review sessions, and I thought that was a great thing. So I've always done it. I believe in it. Do unto others, that kind of thing. Yeah. So let's go. We can take in requests. Check. I wonder how this is being recorded. I wonder if anyone's joined us and collaborating, and all they see is this blank screen.
That looks like one of those things that poppers.
You know what? That beats much better than General Lee from the Dukes of Hazzard.
Yeehaw! What y'all think's gonna happen next? That's always what comes to my mind. Just before every commercial break, they would have the general lead just about making a jump, midair. They'd pause it, and then Waylon Jennings. I never knew the guy was actually a famous musician. Did the voiceovers on the Dukes of Hazzard. You don't care. He's a famous country musician. He was actually he actually was going to be on the airplane that Buddy Holly died on.
Oh, crap.
He actually gave up his seat for Richie Valens and Waylon Jennings, famous guitarist and singer. But that was the voice of what y'all think's going to happen next. There was only 3 channels on it back when that was on. So I think that's why it became a show people want. The main character was the car. Okay, so we haven't, we've done a lot of stuff. We've covered a lot of area here. Let's take a look at the ones that I had mentioned, or one of the ones I had mentioned. That's a good one. We can take a look at both of them. Any of these ones. Here's one. I think I actually asked one pretty similar here on in the fall. You're welcome.
Thank you.
Oh, you're welcome. Okay. So this is definitely so what do you think we'll have to do? Let's read the problem, treat it like an exam. A highway is designed for traffic moving at 65 miles per hour. Those funny people. 65 miles per hour. That make me laugh.
No, I don't do that.
Sorry, that was good. Along a certain portion of the highway, the radius of curvature is 900 feet. The curve is banked, as shown below, so that no friction is required to keep the cars on the road. Please determine the required banking theta of the road so that no friction is required, and then the minimum coefficient of friction between the tires of the road that would keep the traffic from skidding into an early grade at the speed if the curve is not banked. How do you approach this problem?
Slowly.
Slowly. No, it's an exam, dude. Don't go slow. Fast, 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 fast. Moving all the time.
What a free body diagram.
Yes! Sorry, I just interrupted you on purpose. Hope you don't mind. It was for humor. You were saying yes. Newton's second law, right? So let's draw the car. Doesn't have to be a pretty drawing. I could make a pretty drawing. You don't believe me. I could. But that's the best I'm going to do. That's my FBD. What do I need along with my FBD? Oh, I need my IBD. Irritable bowel disease. Which is sort of funny because I haven't mentioned my wife yet. She's a pharmaceutical sales rep who does Crohn's and colitis on drugs. She represents those. So I know a lot, way more than I want. Way more than I want to. Like a large amount more. Okay, so we can put the weight on here. We're getting points as we're going along here. We're getting all kinds of points. And here's the weight. Did they give us the weight? I hope they did. No, they didn't. Interesting. Let's go mass times gravity. See, we have like a little angle theta thing going on here. Blue, we run these blue. Use this other green. I can't really quite tell the difference between these two greens, really. So let's just put this over to the side here. There's a theta going on. What do you think we should do? I say we get some points by making miles per hour into feet per second. What do you say? Sure. So we have the speed at 65 miles per hour. So we go 5,280 feet per mile divided by 3,600 and get ourselves some feet per second. Well, what is the principle, do you think, that's going to make this thing either slide off the road or not slide off the road?
Normal?
Ooh, centrifugal force. So, or you were saying normal force, right? Centrifugal. So it's the centrifugal acceleration, right? And what direction is that going to happen?
Left.
It's going to go left. So the thing that might not occur to you is that this really is kind of a three-dimensional problem, right? So that's, you know, in some of these, well, we have to kind of look down. We have to kind of look down onto the car and see. Okay, well now we can see that's the direction of the normal acceleration right there, right? Because they're going around a curve. I really like red most of the time for acceleration. Okay. So we're going to have an acceleration that way right there. So we're going to have mass times the normal acceleration. And we know that that normal acceleration is going to be v squared divided by rho. So we're going to have a normal force right there. And we're treating it like a particle, so it doesn't matter that there's two onto them. They're a particle. I'm going to go ahead and we're going to reuse this FBD. So I'm going to go, okay, so required banking angle on the road so that no friction is required. So we're going to draw friction on here, but then we're going to set it to 0 for part A. Is that okay? So we just want to reuse it. Might want to draw it twice if we were going to be really technical, but in a solution I would post, I would usually probably draw it twice. Just one time without friction as part A, but here it would be. So between the tires and the road, that would keep the traffic from skidding at this speed if the curve is not banked. Okay, so in one way we'd say, oh, it would be skidding off that way if it wasn't banked. Oh, wait, oh, it's not banked. No, we have to redraw this because it's going to be if it's not banked. Oh, never mind. I'm sorry. So let's go back to this right here. So our coordinate system, we can actually choose two different things. We can go to the x and y, where we have it aligned with the bank. That's one option. Or we could go to what we'll often call the normal and y, right? So this would be, I guess I could call this En if I wanted to, and I could call this J, I don't know, call it K if you want to, doesn't matter. So this is the way that I decided to do it. It'll work itself out. So I go to the sum of the forces in the normal direction is equal to mass times acceleration in the normal direction. And I should put in a little bit of geometry right here. That right there, that angle is going to be the same one as this angle right here, right? Just close them down just to check, right? As that thing closes down, that closes down, so they must be the same angle. So the only thing that's really keeping this thing in the n direction is going to be mg times the sine of theta, right? It's going to be equal to mass times, you go v squared over rho. Because that's the normal acceleration. And thank goodness the masses didn't matter, because they didn't give it to us. So we have that it's 95.33 divided by, what do we say? 900 feet. And therefore theta, that's supposed to be squared, sorry, squared. And, ooh, well, that's a small number, huh? Invalidated. Okay, we did something wrong. I did something wrong.
You forgot gravity.
Oh, thank you.
Just looked at it, moved it.
Having a tough day, rough day, rough day, rough day. Thank you so much. See, you learn more from all my mistakes. Is that how I'm rationalizing that today? Okay, that's better. So I say that this is a lot of bank, by the way. That's, if you were to stand on this, you'd be like, what the hell's up with this road? Good thing there's friction. So now we got to do part B, FBD, IBD, that was terrible. Make them look a little bit alike. And still doing this right here. I guess I want EN over there. J, I'll keep it consistent. So quietly. MG and FN. But now, if we're assuming we're as that diagram and that we're looking in that direction right there, this thing wants to slide this way, so friction must be going that way. But you could also, later on, you could just see the match over here and here when we go to the AN right there. So this is the friction. And I think we can all agree that Fn is equal to the weight mg, and therefore the friction force is equal to mu times mg. So we want to find the minimum coefficient of friction, so we're looking for mu. Between the tires and the road that will keep the traffic from skidding at this speed, right? So they're going at the same speed. So now we, once again, do the summation of forces in the normal direction. It's equal to mass times acceleration in the normal direction. So we have mu mg is equal to m v squared over rho, or mu. Fortunately, masses cancel out. That's great news. It's just going to be v squared over rho g, or 95.3, can't read it anymore, 33 squared over 932 point. And I hope this is a number less than 1, because it's got to be. This magic sticky.
Could you have done a shortcut and just taken the sine of the angle?
You're right. There's a lot of shortcuts, and unfortunately, a lot of textbooks in their solutions will just take these shortcuts that don't show you where they came from. And I don't think there's, I think that kind of makes it seem mysterious to a lot of students. But if you recognize it, I would prefer that you, when solving an exam, that you demonstrate that you knew where the thing came from. But when it comes to friction, the angle and the coefficient of friction are second cousins to each other because they just work out that way. So sometimes in that section of statics, they will play that game and you're supposed to memorize the thing. I'm no good at memorizing stuff, so I'm biased to actually understanding the thing. This is a pendulum, apparently, that's swinging around. So the velocity of the bob required to keep it at this arc. It's interesting. Oh no, okay. So I took this. So I screen captured some of these things. So that 4 feet. This it might have been actually better to leave this out there, you know, without knowing that. But you could do a variety of turning this problem on its ear that can make it like, well, I don't know how to solve that now, but it's just not. Once you see this solution, you could kind of maybe try to imagine when you can be asked a question. I don't have any plans to ask this question, but I would merely point out to you that I have asked a similar question on an exam before, and students were like just totally thrown because I asked it like, oh no, I guess I did. I think I asked what velocity the bob was required to do this right here, and what the tension in the, actually this is probably almost identical to the question I asked. And it is the second cousin of this problem that we just did, because it's, once again, you have to recognize that you have to look down onto this thing to start with, so you can recognize that that's where the acceleration is. So when you go to do the problem, we start with an FBD and an IBD, and draw on this one, we draw it right here, FT, right? Because we got to cut it. And I'll say that's the normal direction and that's the y direction. We have M-A-N. MG going on right there. So it's actually, it might be easier to solve part B before part A. Can you see that? Because we're in the y direction, we can get the tension first. Like a little easier to do. So summation of forces in the y direction equals mass times acceleration in the y direction. There is no acceleration in the y direction. So we go Ft, and by geometry, double check this right here, 30 degrees that way, must be the same thing as 30 degrees that way right there, right? So Ft times the cosine 30 minus, and they give us 10 pounds, okay? And Ft (10) divided by cosine of 30. Or 11.55. Ooh, that was a terrible 5. Definitely a Friday 5. And those are pounds, not newtons. And we said, okay, so the sum of the forces in the normal direction equals mass times acceleration in the normal direction. Normal direction's to the left, positive. So we will say that we have our 11.55 times the sine of 30 is going to be equal to our mass, which is going to be 10 over 32.2. Oh, yes. And then we want the velocity, right? Sure. That's the thing we're getting. And then this distance, they did that for us. We know the length is 8, so we're able to get the 4 feet. So 30 times sine times 10. I almost want feet per second. What if I asked you, in a cruel way, what are the RPMs of this? Go ahead, I'm sorry.
So I just don't understand how, in like the free body diagram, in the sum of forces in y direction, how come it's not like mass times gravity? Like, is it just 10 pounds?
Because the mass of the thing, you would divide the weight by gravity,
How do you know?
and then you would multiply by gravity again.
How do you know that it's the weight of it and not the mass?
Quite often what I would do in SI, I would write the mg, but in US units I would just write the W. So that maybe that would be the, I don't know if that's a sufficient answer in some
So
ways.
like it would be labeled weight.
Like I would label it weight.
Okay.
Yeah, yeah. So I just, by sometimes it's a habit, I write mg.
Mm-hmm.
Yeah.
Oh, I was just confused on like how in the diagram.
Gotcha. The diagram should match the equation, I agree. Yeah. What if I asked you for the RPM? And that's kind of jumping ahead, but I don't think so. Maybe. We just had that class, or at least some people just had that class, where we had, right here, we would know, this is the velocity that we just found, right? If I label the velocity on here. And so, let's ignore that that was an acceleration right here. We would say that this is the omega that we would have. And so the velocity would be equal to omega r. So omega would be the velocity divided by r. Or you would have r 2.538 divided by 4 feet. And so then you have 4. So we're having 0.6344. But these are radians per second, and we would rather have RPM. Usually we use a little lowercase n. So we go 0.6334, and there are 2 pi radians
Per 1 rev.
per revolution, and we want revolution. So we would take and divide by 2 pi to get radians per revs. And then, but we would want 60 seconds per min right there. So that's going to get us something larger than 1. So we're going to say, okay, this is 6.058 revolutions per minute. Or you could say that it takes 10 seconds to make a revolution. See, then to me it makes sense, that I can picture the thing, right? It seems like a real thing to me if I could put it into terms that like I have some kind of visualization, something to match it to reality, yes. That's pretty damn slow though. Of course it is 8 feet long, so that's a pretty darn long thing, so I guess I guess I could see that. It would fit in this room, though, right? We could swing it in this room onto the thing. Yeah. Taking requests. You're worn out. You're burned out. You're so tired. I'm so sick of dynamics.
All right, thank you.
You're welcome. You're right. Have a great weekend.
Yeah, you're doing oblique collision?
Say again?
Oblique collision?
Yes. It'd be a very tough one to select for an exam because it has to be just the right setup of the thing so it doesn't take too much time. It has to be just right. So I have seen professors that asked ones that were like, I don't think I could do that. No. I don't think none of these professors, neither of these professors. By the way, I don't know if you know, Dr. Orlup and Dr. Enrico and I, we work really well together. We like meet all the time and talk to each other all the time. So I'm really happy with our working relationship.
Are you saying it would be fit for exam, or it wouldn't be?
I'm saying I would have to pick one very carefully so as not to make it too time consuming. By the way, these are real exam questions, so I think I found one right here that I think took too long. Okay, so this one seems like it could be a candidate because it's not too much of a twist onto the thing, and if the coefficient would determine the final velocities of the two pucks, express these as vectors. I don't know. This is pushing the boundaries, but it's an oblique it's an oblique problem. It can be done. It just, you want to. I probably wouldn't recommend the coordinate transformation unless you were told to use a coordinate transformation. But let's just take a look at the thing. We have the initial, the impulse, and final. And we'll draw on this, the big squishy. And let's see. Okay, so looking at this, you see that it's going at 4 meters per second, and this is B, and this other one's A. And do they have the same? They're two pucks that have equal mass. Then I'll simplify it a little bit. That makes it just ever so slightly easier. But this one, we could say that we could look at it right away and break this down and go MB times VB1 normal, and here's MB VB1 tangential, and here we go MA VA1. We can label it as normal, but that's the entirety of it. And then I'll define, it doesn't matter which direction we go. So, it makes me feel good to have them aligned with X and Y, less thinking involved if I turn the thing around. So that makes me feel good. So I'll pick both of them going to be moving in the positive direction. So there's MB VB2. That's a terrible V. Terrible V. MB VB2 tangential, and then this is MA VA2 normal. We don't get these orange enough, so I'm going to go ahead and write this in orange, but who cares? I don't know what I just did there. Whee! Have a good weekend.
Thank you.
And so, and we decided, look, this could be a negative MB VB1 normal. Oh, come on. Kind of. Plus MA VA1 normal equal to MB VB2 normal plus MA VA2 normal. Right here is where we can make our, well, I'm going to use theirs. Boom, 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 boom. That was nice. So we have 30 degrees. This is going to be the cosine of 30 degrees. So it's negative 4 times the cosine of 30 degrees plus, this one's 5. And it's going to be equal to VB2 n plus VA2 n. Oh, you can hide purple for me too. 5/430 cosine times minus. And we end up with 1.536 is equal to VB2 n plus VA2 n. We call that equation 1. Now we're set up for our coefficient of restitution, where we would say E is going to be equal to VB2 n minus VA2n divided by VA1n minus VB1n. And 0.8. So 0.8. And this one is going up 5, right? But this one's going down. We never found out what that was, but too lazy to do it now. All right. So 430 cosine times 5 plus 0.8 times. So you get 4.371 can be equal to VA1 normal minus VB1 normal, and that's equation 2.
You talked to me VA.
Did I do it
It
wrong?
would be VB2 minus VA1.
You're right. My bad, sorry.
Because you have the same thing.
Thank you so much. V. Did I do this right now?
Yeah, it's B2 minus A2.
Thank you. Good example. What not to do. If you've ever been to my office, I have one of the demotivational posters. You ever see demotivational posters? They said, mine shows a sinking ship. It says it says mistakes. It could be that your purpose is only to serve as a warning to others. It's hilarious, trust me. I bought it and framed it, put it up in my office. As a ship, I like ships. Kinda, I don't know, kinda got tired of it. So anyway, I'd probably solve this one. VB2n is equal to the 4.371 plus VA2, and stick him back into the thing. So I get 1.536 equals 4.371 plus VA2n. I wrote a 2 there, I said. But then I could have actually just done that in my head, right? So it's right, it was. So it's going to come over to the side. So I'm definitely going to get a negative number here. And then divided by 2. So I end up getting VA2n is equal to negative 1.418. Are these use meters per second? And then I can, from that, I can find my B2n is, I can just add that to my 4.371 and get that this is 2.953 meters per second. And the way the question asks is we're going to express these as vectors. So if the coefficient of restitution is 0.8, determine the final velocities of the two pucks. So I can say my velocity, first off, of A
going to be, and it says as vectors, so he might mean unit vectors. Or they could mean, it just means it has to be an arrow, right? You just have to have a direction. So I would say that we're going negative here, so 1.4, call it 2 meters per second down, right? Because we got negative. Went up, boom, but it's coming back down. And then this one you could express as, this would be technically correct if you said that it was going to have, well, we never wrote out what it was, right? But VB1 tangential is VB2 tangential, which is going to be the 4 times sine of 30, which I believe is going to be 2, right?
Yeah.
So you have 2I plus 2.953J, or I would prefer personally to know the angle of the thing, the magnitude and angle. So 2 squared plus 2.953 squared. So you have 3.567 meters per second, and we're going to have an angle of inverse tan of 2.953 over 2, something larger than 45, 2.953. We get 55.89 degrees. So I kind of would prefer personally to ask it as, and get 3.57, let's go with 3 sig figs, meters per second, and it must be going up and to the right, right? Because it's going, yeah, these are both positive, so it's in this quadrant, and we get 56 degrees. So that's how I would kind of like to have it. But you'd be technically correct for that. Is it too long?
Easier without a transformation.
Yeah, without the transformation, definitely isn't going to be nearly as tediously and time consuming. Got 10 minutes. So any time for one more. We did Newton's second law. Did a couple of them. Did work energy. I think we're okay with collisions. Let's see what this one was. This was like an average impulse force. Yeah, it's not that hard to do. This one boggled my mind a little bit. I didn't actually solve this one, so let me think if we could think this one through together. By the way, this is such a classic like dynamics problem. Like one of the ones that like you know the FE is the fundamentals of engineering. It's an exam that you take your senior year. You should take your senior year, and if you want to try to get a professional engineer's license eventually. It takes about 5 years working in industry before you can sit for the PE, the professional engineer's license. The first stage is to take the FE. And the FE is like a good measure, I think, of like, what was my college education like compared to everybody else, right? To see, okay, it's a tough thing to do, and you really should take a review class before you take it. I'm trying to organize one maybe for coming up, so probably be ready by the time you guys are. If you're for mechanicals, there's already one for civils. I just ran the dynamics one last Friday for Dr. Enrico. But anyway, there's these type of questions get asked a lot, or a lot of times professors are very, hey, I'm just going to look up in some FE equation booklet things, like this one right here. This is in the book, but that kind of thing where people are walking along a boat and then jumping off, it's an impulse and momentum equation problem. So the one that I was looking, so it's not identical, but it's kind of similar in there's conceptual things going on to be able to ask this weird one right here. What I'm going to start doing is having students read them. I hate reading out loud in front of people. I had a reading problem when I was younger, and it's like very embarrassing that I stumble when I try to read something in front of people. But anyway, a Jeep and a car are connected by a tow cable, which bothers me that it's a chain in the picture. That's not a tow cable. The winch, which should not be moving a chain on the Jeep, is turned on and pulls the tow cable at a constant 2 meters per second, which means that's the relative velocity between the Jeep and the car. If both the 1.5 megagram car and the 2.5 megagram Jeep A are free to roll, they're in neutral. We want to find the velocities of the Jeep and the car at the instant they meet. If the tow cable is 5 meters long, how long does it take for the vehicles to meet? How to even approach that problem? Because that's different than anything you've ever seen, right? That's what makes it a good exam equation, because it's going to make you think. And how is your dynamics thinker working so far? And that's what the problem's measuring. I'm not trying to say, oh, can I trick you? Can I trick you up? But this is, someone at the must thought that they must. No, I'm embarrassed that I just did that. I feel humiliated for myself. So how do I even approach it? Well, I draw a diagram. Draw a diagram, and by drawing the diagram, it'll start to go, oh, I get it. Perfect dynamics question. Perfect dynamics question. This is making you think. Not an FBD. We're talking impulse and momentum. Wait a minute, how do I know it's impulse and momentum? Velocity and mass, yeah. Velocity and mass are the key things. And so as I'm going...
It doesn't have a spring, so it's not working.
That's right. Okay. Hey, that's just as good an answer as any, right? As we're playing problem detector. So we have, we always have a choice. We can separate these things out from each other. We could separate them out. It would be nice to not separate them out. Okay. Summation of moments. Almost screwed that up. Moments, momentum. Oh, wow. Good thing this is ending. I'm going to go right to my car and go home. So I can eat dinner and pack up and go to the gig. And move a lot of equipment. I like this venue, except that it's upstairs. They have an elevator, but it's a weird thing that you have to go up. I own the PA, which is it's always a weird thing called a public address thing as the PA. It's a bunch of frickin' speakers. All right, so back to this. What's the initial momentum? 0. What's the impulse? It's 0. You say, what about the tow cable? Ah, but it's part of the system. Part of the system. Okay. So 0 plus 0 equals, but we can label this diagram and we're gonna go, well, this is gonna go that way, and that's gonna go this way. So we're gonna have the mass of A times the velocity of A, and we're gonna have the mass of B times the velocity of B. And this is gonna be 2 and 2. All right, so MAVA2 minus MBVB2. All right, we got 2 unknowns. What do we do? Let's see. And we can keep the thing as megagrams because we don't care. The units would just cancel out, so we're totally okay. What's the only other piece of information we have?
We have the relative velocity.
Yeah, and it's the Jeep that's pulling it towards there, right? So we're going to say that this relative velocity is going to be, I got to think it's going to be B with respect to A, right? Because that's how B is moving. If you held A, okay, so we're going to get the sign right of this, right? We want to have a positive relative velocity. So we wanted to see if you held A in place,
B would go
this way right here. So it'd have to be negative. That has to be a negative relative velocity if you're saying B with respect to A. So B with respect to A is always going to be written B minus VA. I mean, that's just the definition of this. But we're going to say that's going to be equal to a -3. Did you follow my logic?
It would be -2.
Oh, is it 2? Sorry. Very tired. So here's our other equation right there, right? So this is, by the way, this is going to be 2 and 2. 2. I don't know how to put 2 in there. 2. Sure. So we just say that VB2 is going to be equal to VA2 minus 2. And put them in. And say 2.5 times VA2 minus 1.25 times VA2, and then that's also going to be, what do we have, a minus, whoop, 1.25 minus 2. VA2. And hopefully, if we got the signs right, hopefully we'll get it'll make sense what direction VA is going to go. It should definitely be going to the right. Oh, this was equal to 0, or 0 is equal to it. So, not liking that. Yeah, I screwed it up, I think. Probably because of that. Probably because of the logic that I'm applying right there. Anybody agree that I screwed it up? 1.25 times 2, which you should be able to do in your head. And bring it on to the other side. It's going to make it negative because there was a negative. So to bring it on to the other side. And now we're going to have 1.25 divided by that. I screwed it up. The relative velocity, that is the relative velocity between the Jeep and the car. So, from what way that they're saying is the Jeep in the car. If I held the...
It's got like, the constant V has like notation with it that I can't figure out what that notation says.
Yeah, I still believe in that -2 right there. That would be what B is moving to the left in the negative direction with respect to A. So it has to be a negative value. And did I do this one correct, where I brought him over to there, okay. And then, so I plug him in to here, and that's that negative and that negative cancel each other out. So that should be this 2.5, right? The 2.5 goes to the other side. And I subtract out 2.5 by 1.25 and I get 2, which doesn't make sense to me, that this would be a negative 2.
I don't think it is. So you would move the 1.5 to
Velocity of the Jeep or the car at the incident. There's no reason, I can't picture that thing going to that A would be going to the left. That does not make sense to me at all. It's impossible. But if we're saying that, then you would say that B was going to be 0, right? Or be 4. Because we would stick it back into here and say that we would have no, okay, it's interesting, all right? So like if we put negative 2 into here, we would get what? 2.5 times negative 2 minus 1.25 times VB2 equals 0. And the only way that that could be true is if VB2 was also negative.
I got that the VA2 is 1.25.
1.25? Okay. Maybe I'm just doing math wrong because I was just tired. Shouldn't you take 1.25 times 2?
That's 2.5.
2.5, bring him on to the other side. And he's going to be negative. You agree?
No, what I did was, so, wait, let me just, I might have done something wrong.
It's all right. But anyway, I'm going to go, okay, so we'll go 5 divided by 1.25. And I'm saying he's going to be negative 4. Thank you. Now I'm like, these are meters per second, right? Yeah, meters per second. Now I'm very inquisitive here. All right, so this does work out right there in terms of the relative velocity, right? But it doesn't make sense that he would be going left.
I got that, so if it's negative, if you move that over and
Thank you.
Thank you guys, and have a great weekend.
I got VA2 would be like 1/3, I mean 2/3. Who knows?